Alright, so in this video we're going to go over horizontal launched projectiles. Now these are always fun problems because they always say that we're either throwing something or someone's jumping off of a cliff or anything in that sense. So these are pretty cool problems to solve, and you can apply them to real world situations. So let's look at a cliff that's 30 meters off the ground, and let's think of, let's say, a person running, and then we're not going to say jump off the cliff, but just runs off the cliff. So I'm going to draw the person as they're running and getting ready to run off the cliff, and we're going to say he runs off the cliff with a horizontal velocity. So we're going to say his velocity is 5 meters per second. Now the reason why I say he doesn't jump, because we'll touch upon that in a later video where there's some type of angle of how he's jumping. But for right now, he's just running, and he runs right off the cliff, and he's going right into the water. Now we say he has a horizontal vertical component to his velocity because he's going straight out. So if I was to draw his trajectory would look like this. It's not going to be straight down. It's going to look something like this as he falls into the water, and he's going to have a splash at, let's say, that distance. So what is happening while he is falling towards the water? Well, we can draw that, and we'll draw at different time intervals. We will draw his vertical and his horizontal component. So we said in class that his let me rewrite this, that his horizontal component is going to stay constant. So as he's falling, he's going to have a constant horizontal component of 5 meters per second. It's going to be the same size line from the moment he falls off the cliff or runs off the cliff to the moment he lands in the water. So we're going to say that is 5 meters per second. And this is 5 meters per second. Now, how does that stay constant? Well, like we said in class, there is no horizontal force that's either slowing him down or speeding him up. So therefore, his initial velocity, which is 5 meters per second, will stay constant throughout the entire trajectory until he lands in the water. But there is a component that will be switching, and we will draw that in a different color. And that component is his vertical component of his velocity. So we can draw that as going straight down. So we'll draw that now, a different color, going straight down. Just like so. Now this vertical component is getting bigger, larger and larger as he goes down. Reason being, there's an acceleration, and the acceleration is due to gravity. Since we have an acceleration, so we'll put that, since AY, his acceleration in the vertical plane, is 9.8 meters per second squared, his velocity vertically will increase, like we showed through our vector diagram. But how much will it increase? Well, that's what we're going to figure out. So what we can figure out is, let's figure out what his velocity final is in the y direction. Let's figure out his displacement. So his displacement, let's say, in the x direction. And let's figure out how much time he will be in the air for. And all we need to know is the height of the cliff and his initial velocity, which is 5 meters per second horizontally. So for the first question, let's take the time. The time is the simplest to figure out. So let's put time, we'll do time in air. Okay. Now how are we going to find the time in the air? Well, let's think about what equation we can use. Check our reference table. So we can use the equation D. Now remember, when we're talking about projectiles, we have to specify if we're talking vertically or horizontally. So in this case, we're talking about the distance in the y direction equaling the initial velocity in the y direction times t plus 1/2 a in the y direction times t squared. So let's put all the information that we have in. Well, we know the distance in the y direction. That is the height of the cliff. And that is 30 meters. So we can put 30 meters here. And that's equal to the VI in the y. Now we know since the person ran off the cliff, he didn't jump and he didn't jump straight down. He ran horizontally 5 meters per second off the cliff. That the VIY is 0. There is no velocity component in the vertical direction. There's only a horizontal component. So that's 0. Therefore, that time, which is right there, gets canceled out and becomes 0. We have then plus 1/2. Our a in the y direction, the only acceleration in the y direction is gravity, which is positive 9.8. The reason why we're saying it's positive is because we're choosing the down direction to be positive, and we are solving for time. So this was the correct equation to use, since we have only one variable left, and everything else has been substituted in. So we have 30 meters on the left-hand side of the equation, equaling 4.9 on the right-hand side times t squared. We could then divide by 4.9. We divide by 4.9. And we can see that the time in the air will be equal to 6.12, and that is t squared. So since t squared equals 6.12, in order to get t by itself, we need to take the square root of 6.12. So if we take the square root of 6.12, that will equal our time. So what does the time equal? The time will then equal 2.47 seconds. Alright, so now that we know the time, now we could find the displacement in the x direction. So we can write displacement in x direction. As I'm writing this, I want you to think about what equation we're going to use. Alright, now, if you figured that the equation that we just used we're going to use again, that would be correct. However, what's the difference? Well, we're going to use the same equation. Let me write the equation as d equals vi times t plus 1/2 at squared. Except this time we're talking about the x direction. So all the variables will get a sub variable of an x. So it becomes the displacement in the x direction, the velocity initial in the x direction, and the acceleration in the x direction. The reason why we don't put time in the x direction, because time is universal. Time doesn't have a direction. So when we label all our variables in the x direction, now we can fill in the information that we have. What is our velocity in the x direction? Well, we said that the person, as he runs off the cliff, is traveling at 5 meters per second. That's horizontal. That's the x direction. So dx, displacement in the x, is equal to 5 meters per second times our time. And we said our time was 2.47. So that's 2.47 seconds. And that's plus 1/2. Our acceleration in the x direction is what? Well, our acceleration is 0. There is no acceleration in the x direction. We are moving at a constant. Now, since that is 0, the entire expression after the plus sign cancels out. That becomes 0. So we're left with that the displacement in the x direction is only due to the initial velocity of 5 times the time, which makes sense. The x displacement is only predicated on how fast you're going in the horizontal for how long. And we get that our dx, our displacement in the x direction, is equal to 12.35 meters. And we'll box that. And finally, what is the velocity final in the y direction? Or we can say vertical direction. Alright, so what equation will we use to find v final? Well, let's look at all of our equations and see where we have a variable, just v final. Alright, well, we see if we have the time and the acceleration, we can calculate v final. So we'll use vf in the y direction is equal to vi in the y direction plus at. And remember, a has to be in the y direction. So v final is what we're trying to find in the y direction. And that's going to be equal to 0 plus 9.8 times the time. And we said the time was 2.47 seconds. Therefore, the v final in the y direction, v final y, is equal to 24.21 meters per second. Alright, so just a quick review. We said when we have a horizontal projectile, we know that Vx is constant and Vy changes, and we said that's due to gravity. Due to acceleration from gravity. Okay. The only other thing that we need to know is that time is universal. Time, you could say it's universal, or you can say has no direction. And the last thing we can say is, when it comes to formulas, we must break up the formulas. So just we'll make that must specify direction when using formulas. If you can remember these key facts, you should not have a problem answering a horizontal projectile problem. Alright, so in this video we'll discuss a projectile being launched from an angle. So if you look at our picture, we have a cannon being fired from the surface at an angle. And we'll say, let's say this angle, we always say this angle from the surface is known as theta. Okay? Now just like the first problem, since there is no force working on the object in the horizontal direction, we say that the horizontal component of the initial velocity stays constant. So if I was to draw, let me use my arrow, make things a lot easier. Alright, I'll use my arrow. If I draw an arrow, these components, the x component of our velocity, will all stay the same. They will not change. So I'm going to draw on all of them. This component stays constant. Because in these problems, we neglect something that's very important. We neglect air resistance or any type of wind. So since we're neglecting that resistance, we say that VI stays constant in the horizontal direction. So this would be Vx, and this would be V. Let me rewrite that. Sorry. This would be Vx, and this would be Vx, 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 and Vx. So we can say this. We can say that the initial velocity, so Vix, will equal Vx through the trajectory and will also equal V final x. Just like that. The direction stays the same throughout the entire trajectory of the projectile, and the magnitude stays the same throughout the entire trajectory of the projectile. But what about the Vy? So in a different color, we'll make another arrow. We will make our Vy. What happens with the Vy? Well, initially, the Vy is going to have a component. Why? Because the angle, the velocity has some type of angle. So let's draw the velocity first at that angle. So if I was to draw an arrow to represent V, here is our initial velocity. And maybe I should do a different color. So let me do a different color. We'll make that, let's say blue. Okay. We'll make a nice arrow right there. There is our V. Okay. So we can call this V. Okay. So this is our velocity. Okay. So let me just change what we have up here. So everything stays consistent now. Okay, we said the Vix equals the Vfx. So let's delete the Vx and let's just make Vfx. So this is just say the Vix equals the Vfx, which then equals the Vx throughout the entire trajectory. Alright, now that makes sense, and now we're consistent. So now we can draw that Vx. So let's draw that Vx. So that Vx we'll draw in orange. We'll have a nice orange line now. And there is our Vx right there. We'll label it as V sub x. Now what about our Vy? Well, initially our Vy is where? So we'll draw that in a different color. We'll draw that in purple. Our Vy can be drawn right here. We have a nice arrow like this, and we'll label this V. We'll label this right here Vy. So that is our velocity component in the vertical direction. We have our velocity component in the horizontal direction, and we have our V velocity vector pointing straight up at some angle theta. So if our velocity in the x direction stays constant, what happens in our velocity in the y direction? Well, the y direction gets smaller and smaller. So we can see at this instantaneous snapshot of the cannonball, it's a little smaller. And at this one, it's even smaller. And at this one, it's almost 0. And at this one, it would be 0. There would be no Vy. In this one, let's see how I draw it and see if you could pick up on what exactly is happening to the velocity in the y direction. Let's see if you can figure it out before I tell you. So I'm going to draw it on this cannonball right there. And finally, on this cannonball, we'll have a Vy like that. So what can we see? Well, we can see that the velocity vectors are very similar to the cannonball, the instantaneous snapshot of the cannonball on the other side of this parabola. So if I was to draw the trajectory, let's draw the trajectory and we'll name it. We'll do that in green. So I'm going to draw the trajectory of this cannonball. So the trajectory looks like this. Well, you know what? I'll do it right under the cannonball so you can see what the trajectory looks like. Well, there's the trajectory. And if we think about these cannonballs as snapshots, whatever happens on one side of this upside down parabola will happen on the other side. So I'm going to draw these lines, and these are at the same time interval of going up as coming down. And what's happening? Well, we can see Vx is the same. Vy is the same, but opposite in what? Opposite in direction. So we can say that Viy is going to be equal to Vfy, except opposite in direction. And we show opposite in direction as negative. So if we look at the initial velocity in the vertical component, we see it's pointing straight up. We can look at the velocity final in the vertical component, we see it's straight down, but it's the same magnitude, just opposite direction. Now, why does the velocity slow down and become 0 at the pinnacle? So let's draw the pinnacle. I'll draw the halfway mark. I'll use an arrow. If this is the halfway mark right there, okay, why is Vy equal to 0? Why does why is Vy here equal to 0 meters per second? Well, it's equal to 0 meters per second because of the acceleration due to gravity. So I'll draw that in blue. There is a constant acceleration vector downward, and this we call g. It's gravity, and that equals 9.8 meters per second squared. So that acceleration downward is going to slow down the vertical component of the velocity as the projectile goes all the way up, and at its pinnacle, at its top height, it will equal 0. The velocity in the vertical direction will equal 0. But as soon as it passes the max height, it's going to continue. It's going to start to speed up again, and it's going to speed up at a constant rate. Now, why does it speed up at the constant rate? Because gravity never changes. Gravity is constant at 9.8 meters per second squared. So it's going to accelerate that projectile at the same rate that it slowed it down all the way back to the surface. That's why the initial velocity in the vertical direction will equal that final velocity in the vertical direction, but opposite directions. At first, it was shot up, but when it comes and hits the ground, it's going downward. Alright, so knowing this information, we should be able now to answer some questions on projectiles being launched from an angle. The only other thing that you may need to know is that the y displacement, well, let's put that in a different color. Let's make it, we could do green since we're talking about displacement. The y displacement is the height. So it's from here down. This would be the y displacement. So we could say y displacement. It's the y displacement. And from the initial starting position all the way to the end, we can say that this is the x displacement. This is the x displacement. Again, when we are working with the formulas that we are given on the reference table, we have to make sure that we only use the information in the vertical direction and the vertical in the horizontal direction. We cannot use parts from the vertical components and parts from the horizontal components. The only thing that we can use in both equations is time, since time is universal. Alright, so let's try some problems. Alright, so for this question, it says, you kick a soccer ball at an angle of 40 degrees above the ground with a velocity of 20 meters per second. You want to calculate how high will it go, how much time does it spend in the air, how far away from you will it hit the ground, aka the range, or the x displacement, and what is the ball's velocity when it hits the ground. Okay, these are all questions that we can answer now that we understand exactly what's going on with projectiles. So the first thing you want to do is you want to draw a diagram. So let's draw exactly what's happening here. So if I have a ground surface, which is right here, alright, I'm going to put my soccer player right here. So there's my player, and he's about to kick a soccer ball. Here's the soccer ball, and he kicks it with an initial velocity of, we said 20 meters per second. So we will say this is 20 meters per second, and that the degree measure is 40 degrees. So we'll put 40 degrees. Perfect. Alright, now once we have our picture, now we have to put our knowns and unknowns. So we want to make our chart, knowns and unknowns. So here we go, knowns. Now we have to remember when we're writing our knowns that we have to specify our knowns in the x direction and in the y direction. So these are our knowns in the x direction. So I'll put x direction. Let's make sure we write it. Direction. Alright, so now what are our knowns in the x direction? Well, we know the x component of the velocity, the initial velocity. So we'll say Vix is equal to what? Well, we know that the Vix is equal to Vi cosine theta. And now we would draw Vix. So that force vector will be right here. Okay? And we'll label it as Vix. Great. What else do we know? Well, we know that the acceleration in the x direction, a acceleration, is equal to 0. There is no acceleration. There's no force working on that soccer ball when it takes flight. So the Vix will stay constant throughout the entire trajectory. It will not change. So the velocity in the x direction will not change. Do we know anything else in the x direction? No, we don't know anything else in the x direction. Alright, so now let's put y direction. Let's put our knowns in the y direction. So we'll say y direction. Okay, and what are our knowns? Well, VIY is equal to the VI times the sine of theta. And since we specify what that's going to be, let's draw our vector. That vector will be right here. And we can label it as VIY. Beautiful. What's our acceleration in the y direction? Well, our acceleration is equal to 9.8 meters per second squared. Okay. Or negative 9.8 meters per second squared. Now, the reason why we have to use 9.8 and negative 9.8, or at least know that we may have to use both of them, is depending on what we're going to choose as our positive direction. Is up going to be positive or is down going to be positive? And we'll go over when to use 9.8 or negative 9.8 when we are doing this problem. But for our knowns, let's put down both. That the acceleration could be 9.8 or it could be negative 9.8. Do we know anything else? Well, we have our acceleration, we have our initial velocity. Nope. We put all the information that we have been given. Okay? So now, what are our unknowns? So let's write our unknowns. Unknowns. Okay. Again, our unknowns are what we're looking for. And like before, they have to be either x direction or y direction. How high will it go? Well, is that a vertical question or a horizontal question? Well, height is a vertical question. So that will go under our y direction. So we can put how high will it go as dy. So we will say dy equals question mark. What about question number 2? How much time does it spend in the air? Well, that could be an x or a y. So we will put time under the y. And we can also put time under the x. It works using both information. How far away will it hit the ground, aka range? Well, the range is the x displacement. So we will have to put dx and question mark. And finally, what is the ball's velocity when it hits the ground? Well, now could be a tricky question. In order to find the component, in order to find what the final velocity is, we need to know what each component is. So we can put the final velocity vfx over here, and we are going to have to find also v final y. Alright, so we'll answer the first question. A says, how high does it go? So that would be dy equals question mark. Now, how do we find a dy? Well, we use the equation vfy squared equals viy squared plus 2ad. And that would be dy. And we have to remember it's also ay. So why do you use that equation? Well, we have all of the variables except for dy. Now, someone might ask, but we don't have the final velocity. We do. It's not the final velocity of the trajectory, it's the final velocity to the height. Because we know that at the pinnacle, at the top height, the final velocity in the y direction has to equal 0. The object is not moving vertically at all. It's 0 meters per second in the vertical direction. So that's 0 squared. That's equal to, what's our VIY? Well, we said our VIY was equal to our velocity, which is 20 meters per second, times the sine of theta, which is 40. And that entire thing is squared. Okay? Now we add to it 2 times the AY. What's our acceleration in the y direction? Now that is when we use negative 9.8 meters per second squared. Now why do we use negative 9.8? Well, we said that our velocity is going up. So we're choosing up as the positive direction. Since our velocity is going up and that's positive, the acceleration which is coming down is impeding our velocity. It's slowing it down. Therefore, we have to show that by a direction change. So our direction of our acceleration is down. Therefore, it is negative. And that is times by d sub y. When we figure these computations out, we get 0 is equal to 12.86 squared plus 2 times 9.8 dy. When we further break it down, we get that 0 is equal to 165.27 plus 19.6 dy. Finally, since we have to separate so that we get dy by itself, we subtract 165.27 from one side, 6.5. Oh, sorry about that. negative 165.27 equals plus 19.6 dy. And we get that negative 165.27 is equal, remember these are all negatives. So this is negative, this is a negative, this is a negative, negative 19.6 dy. We divide by negative 19.6, divide by negative 19.6, and we get that dy is equal to 8.4 meters. Alright, so now we'll try to solve how long does the ball stay in the air for, so the time. Well, since we don't know the displacement yet in the x direction, we can think about this in terms of the trajectory. Now, from the previous slide, we said that the trajectory is a parabola, and that we know that at any instantaneous position on the parabola's left-hand side, it's going to equal the right-hand side. So the time it takes for the projectile to reach its pinnacle or its height is going to be the exact same amount of time it's going to take from that height to hit the ground. So we can say that the acceleration due to gravity, AY, so we'll write AY, will equal the final velocity in the y direction, the initial velocity in the y direction, over that time. So when we rewrite the formula to solve for time, we get that AY times time equals VF minus VI. Again, this is the y direction. And then ultimately we can write this equation as time equals V final y minus VI y over the acceleration y. So we get that t must then equal 0 minus VIY, which we found to be 12.86, divided by negative 9.8. Again, it's negative because it's impeding that velocity that's going up. I'll erase our horizontal just so I can fit some more computation. And we see that time must then equal 1.31 seconds. Now, I'm not going to box this because this is not our answer. This is the time that it takes to reach the height. So what's the total time? Well, like we said, the total time will be double this. So we will take this answer and we will multiply it by 2. And when we multiply it by 2, we get that the time will equal 2.62 seconds. And now that's the answer I can box. So the total time will take 2.62 seconds. Alright, so the next question asks, how far away from you will it hit the ground, aka the range? We want to find the dx, displacement in the x direction. So, since we have now the time, we can use the equation dx equals the VIY, so we could say the VIX times the time plus 1/2 AX times t. Now when we fill in the information, the range will equal our VIX. Now, what's our VIX? Well, we said it was the VI times the cosine of theta times the time plus 1/2. What's the A? We said the AX is 0 times the time. So that cancels that entire expression out. And we are left with that the range or the displacement the x is equal to 20 cosine 40 degrees, and the time is 2.62 seconds. When we figure that out, we get that the dx is equal to 15.32 times 2.62. And finally, that the dx must equal 40.14 meters. And we could box this. Alright, so the final question asks, what is the final velocity when the ball hits the ground? Well, now that we wrote in all of our information of 40.14 meters is the range and 8.4 meters is the height, now we can find that final velocity. So let's draw exactly what the final velocity would look like. So we have our components here, and I'm going to draw an arrow going this way. This is our horizontal component, and we'll label this as VF. Well, let me put it on the other side. We'll label that as VFX, and we know that that is equal to our VIX because it doesn't change. We'll make our next arrow going down, and we'll label that as VFY, and we'll have a nice blue arrow to show our resultant velocity, and we'll label that as VF. So what do we know about VF? What is VF equal to? Well, we said that since this trajectory is a parabola, at the instantaneous snapshot of our starting position, which is 20 meters per second, the ending has to equal the same thing. So we know that the magnitude of our final velocity has to be 20 meters per second. But what did you see change? Look at the snapshot of the beginning. We see the VIX going towards the right. It's the same as the VFX going to the right. But the VIY is going up. The VFY is going down. And because it's going down, the resultant went from up to now down. So the magnitude stays the same, but the direction changes. So therefore, our final velocity is negative 20 meters per second.